Let us try to solve using Smithchart a problem that is given to us, which states that there is an antenna with an impedance of 40 plus J30, which is to be matched to a 100 ohm lossless transmission line with a shorted stub. We've got to determine the stub admittance, the distance between the stub and the load, and the stub length. This in fact happens to be an exercise problem in our textbook Matthew N.O. Sadiku. We have the load impedance, which happens to be 40 plus J30, and we have the characteristic impedance given as 100 ohms. A rough figure of what is actually happening here is going to help us a lot. So we do have a transmission line which has the characteristic impedance connected to an antenna which has a load impedance of 40 plus J30. We may have somewhere in between here a stub of which we are supposed to compute the length between the load and the stub, the length of the stub, and of course the impedance required or the admittance required in this stub. The first type is to normalize all given values. So you have the load impedance. So our normalized load impedance here is going to be 40 plus J30 divided by 100. That is going to make 0.4 plus J 0.3. Now this normalized load impedance is what we feed as input to our Smithchart here. So let us go ahead and try to feed as input 0.4 plus J 0.3 into the Smithchart. So we go ahead, and since we have a plus, we understand that we've got to be concerned about the upper half. So first follow the 0.4 circle, which gives the reactance circle, and then we try to find where the 0.3 semicircle is. That falls over here. So 0.3 and 0.4 falls somewhere over here. This is going to be our load impedance point. Step 2 would be to draw the constant vswr circle. So we go ahead, pick up our compass, place it at the center, bring it down to the load impedance that we have just plotted, and we draw the constant VSWR circle. Once our constant VSWR circle is in place, we pick up our ruler and join the line Once I draw in my line, I can go ahead and find the normalized load admittance. This is the normalized load impedance point. Now that I have the normalized load admittance, as we've seen in the theory, we will be more working around with the admittance while we speak about impedance matching. Step 3 is to read the normalized load admittance. which we have done here, and this happens to be at the point on the real axis, turns out to be 1.6 touching 1.2. 1.6 minus J 1.2 Siemens. Now our step 4 for impedance matching is very interesting. Well, as we discussed in the theory part, we need the normalized load admittance to take a real part, to take a value of 1. Highlight the unit circle, or the circle which passes through 1. So this circle here, let me get a pen and I highlight this circle here. Now this circle means that the real part of the complex impedance or admittance is always going to take a value of 1. So that is where you have impedance matching happening. So taking a look at the constant VSWR circle, you see that there are 2 points. There is either this point here or this point here, wherein you may achieve the real part of this complex admittance taking a value equal to 1. Let me go ahead and mark them as A and B. So we have 2 points. Now, in fact, these 2 points A and B represents 2 points wherein you can have the stubs connected. Remember, we may either have a single stub or a double stub connection. So this is what is actually represented over there. So our step 4 is to highlight the unit circle and find where the VSWR circle intersects. So we compute that as points A and B. Let us read out points A and B from the Smith chart. So point A is obviously 1, and the imaginary part is going to be 1 is over here, 1.1 is over here. So there is this part over here is going to be somewhere like 1.1, so 1.05. Let me go ahead and take that as A will be at 1 plus J 1.05, and B over here is going to be at 1.2 here, 1.0 here, so this is 1.1. So between 1 and 1.1, again B is going to be at 1 minus J 1.05, or the admittance as required. The required stub admittance is going to be, step 5 is going to be read out A and B, or the stub admittance. Let us say they are 1 plus or minus J 1.05 mouse. Now we've got to go ahead and compute the distance between the load and the stub over here. To compute the distance between the load and the impedance matching stub connectivity points, let us go ahead and pick up our roller and connect the center to these 2 points. So this is 1 option that you can have, and this is another option you can have, wherein you can connect the two stubs. So since we've got to move towards the generator, you have to calculate. Okay, so the load is over here, the load admittance is over here. So moving towards the generator, you can reach 2 points A and B. You can move towards the generator, so moving through the constant VSWR circle, you can reach over here. So this is one distance that you can compute, and again moving from this spot all the way through the constant VSWR circle, you can compute the second distance to this spot. So let us go ahead and find where these points are, the electrical length. So on the outer scale, we measure our load to be at this point is 0.3, this is 0.31, so 0.302, this is 0.302 lambda. B is at 0.33, 0.34, so 0.332, 0.334, 0.336, and 0.338, 0.338 lambda. So my spot B, let me call that YB. I can compute the distance. Step 6 is to compute the distance. So to travel this distance over here, you have 0.338 and 0.302 lambda. So the difference is going to make like 0.338 minus 0.302, 0.036, 0.036 lambda. Let me call that my point is B here, so let me call that LB, and I've got to compute this distance over here, so I go ahead and mark this point. This point is 0.16, 0.162, 0.164. We take this as 0.164 lambda. So I've got to go all the way from, so to compute this distance here, I've got to move 0.164 minus 0.302 lambda, making it negative. Okay, I'll just write that part over here. So to compute my distance LA, the destination is at 0.164 lambda, and my starting point is at 0.302 lambda. So my distance here is going to be 0.164 minus 0.302 lambda, which is going to make negative 0.138 lambda. Now distance cannot be negative, and you see that there is this 0 point coming in between. So what we've got to do over here is you've got to add this negative 138 lambda with a 0.5 lambda, because the whole circle is of 0.5 lambda. So plus 0.5 is going to give me 0.362 lambda. So LA is going to be at 0.362 lambda. So if you just look at this figure here, so this this should be point B, because point B is closer, and this should be point A. It just means that I can either have a stub at point B, which happens to be at 0.036 lambda, or I can have a stub at point A, which is going to be at 0.362 lambda. So in case I use two stubs, I would call this a double stub. In case I use a stub at any one of these points, I call that a single stub matching. But ideally, when we go in for a single stub matching, we go with the closer point. You don't go ahead and put a single stub at the at the farthest point, you go ahead and put a single stub at the closest point. If you need a double stub, you go ahead and put it up at these 2 points. Okay, so this is how you compute the distance between the load impedance and the stub connecting points on a Smith chart. Step 7. Now going back to the theory, if you remember, to find the length of the stub, you had to go ahead and compute the imaginary part. And to compute the imaginary part, one of the things we did was to multiply the numerator and the denominator with the complex conjugate. So that is what we'll have to do over here. You'll have to find the complex conjugates of point A and B. Now the imaginary part of point A and B happens to be at 1.05. So A has a complex conjugate which would be at this, because A is at 1 plus, because the imaginary part here is plus 1.05, the complex conjugate is going to be at minus 1.05. So there is 1.0 here, 1.1 here, 1.05 maybe somewhere over here. So this spot here minus being on the lower part is going to be the complex conjugate of A. So let me mark this spot here as A dash. Okay, now A is the farthest point, B is the shortest point, so I'll equally have to go ahead and compute the complex conjugate of spot B here. So because the A or B are your options. So B again is at minus 1.05, the spot here, so its complex conjugate is going to be at plus 1.05, which is somewhere over here. Let me call that B dash. Now to compute the length of the stub, what we've got to do is very simple. You just go ahead and pick up your ruler and mark out these 2 points. Let me pick up pencil, so A dash to the center, or the center to B dash. So my step 7 is going to be to mark the complex conjugates of A and B. So that would make A dash and B dash. This would be on the outer circle, and step 8 would be to compute the length of the stub. You'll have to make one more assumption. You'll have to check if you have a short circuit stub or an open circuit stub. Now on your admittance chart, the rightmost end over here is going to be your short circuit spot, and the leftmost end over here is going to be your open circuit spot. Now since this question we have the short circuit spot, usually we will be using short circuit stubs. So to compute the distance, you'll have to measure the distance from the short circuit spot to A dash. Now measuring short circuit spot to A dash is going to give you the length of stub connected at spot A, and the distance from the short circuit stub all the way to B dash is going to give you the length of stub B. So let us go ahead and compute. Because we're having a single stub here, we'll be using the stub at B. So let us go ahead and compute the distance from this spot here. Now this spot over here happens to be at 0.25 lambda. So from 0.25 lambda I've got to go all the way up here. Now this spot over here falls at 0.12, 0.13, so 122, 124, 126 and 128, 0.128 lambda. So I pick up my calculator. From 0.128 minus, I go to 0.25, which happens to be negative. Now since I do have a negative value, I have to plus the 0.5 lambda. turns out to be 0.378 lambda. So the length of stub at point B turns out to be 0.128 lambda minus 0.25 lambda, which is, I've got to add that with 0.5 lambda, turns out to be 0.378 lambdas. If required, I can as well compute the length at stub A as well, so I can measure the length over here, which turns out to be 0.372 lambdas. So this is going to be 0.372 minus 0.25 lambdas, turns out to be 1.22 lambda. So if required, I can compute the length at A as well. Over here I will have 0.122 lambda, and over here I will have 0.378 lambdas. So this is going to be my solution to compute double stub if required, single stub if required, using a Smith chart without using the analytical method. More later. Thank you.